one important form of relationship that we have today is this idea of neural networks. And there's other forms of artificial intelligence. Some of them use trees, which would be lecture 7. But this one has been gaining a lot of popularity. You know, ChatGPT, all these GPT models, all the image, like convolutional neural networks, which are image processing and video processing. We have cars that drive themselves now. So there's quite a lot of applications of these kind of networks, which are a graph. You can kind of see it here. It's just links, nodes, and then they're linked together. So that's another node, that's another link. And so that's kind of how most of these neural networks are set up. So in a way, they are a node link diagram. They are a relationship, a binary relationship, exactly what this chapter is looking at. So it's one important type of network that people may want to visualize one way or another. So we may visualize it to learn more about, to teach, kind of get familiar with neural networks. You may visualize it to try and understand what the neural network does, which, by the way, it's not that easy. And if those of you who are in this field, there's also a whole, it's been a big movement for the last maybe 5 to 7 years called explainable AI. How can we understand why a neural network makes a decision? Because, like I said, you have a self-driving car. How do we understand why that car goes one direction and not the other? And then you have all this other weird stuff that goes on. People talk about ethical AI. Would that car that drives itself would pick, an old person versus a child to hit if it has no other choice? I don't know. I don't think these neural networks are there yet, and I don't know. You probably can train them on some things, but in general, that's kind of what these neural networks look like. So most of the time, there's some sort of an input layer, and they all deal with numbers. So most of the time, those numbers are between 0 and 1. They try to keep them like that. So if you have something like an image that has a color RGB, that RGB gets converted into some sort of 0, 1 at some point. And then everything that this network has, so each node has a value attached to it. So that's the value that it holds. Like I said, 99.9% of the time is going to be something between 0 and 1. So 0.44 is one value that is going to be associated with this node. And then this links, and I'm not sure if you noticed, but I'll mention it. Each node, generally, they are organized in layers. And nodes on one layer are not connected to nodes within the same layer, but they are connected to all the other nodes on the next layer. So layer 1 kind of keeps going here, and then you can see that there is a connection between this node and all the other nodes there. And so the network will have a lot of these connections. And really the learning part takes place on the edges here. Each of this edge gets some sort of a weight. It's called a weight. What's going to do is going to multiply the number. So let's say there's a 0.5 that this node has. And then let's say the weight here may be 0.9. So this 0.5 gets multiplied with the weight. So what we get is 0.45. And that gets transmitted here to this node. But this node also receives all the values from everyone else, and it kind of, most of the time, it just sums them up, and then it applies some sort of again, once you sum up a lot of numbers, you end up with some that's not between 0 and 1. So they do some sort of, they have a function there to bring them back to 0 and 1. And that's what this node stores inside of it. And so that the weights themselves, so when a network learns, what's going to happen is that these weights of the edges are the learning. If you think of a neural network as, it's something that takes an input that gives you an output. Something similar to that would be a program. You write code. You get an input, the code processes it gives an output. So the code of the network, it's stored here in these weights. It's just there's a lot of them, and when the network, the humans don't really write that code. What they do is train the network, and that changes the code. It's almost like writing code by giving a bunch of examples, and then somebody writes the code inside of it. So the weights of these layers is what makes it, what's important to visualize, because that is the code. It's the equivalent of looking at the code of a program that takes an input and gives you an output. But notice everything is so very hard to look at because there's a lot of them, first of all, and it's just a bunch of numbers. And then the network learns, and as the network learns, these weights get adjusted. There's various algorithms to kind of do that. And when you're done learning, you can use that. Basically, you teach a car how to drive first, which instead of writing program code for the car to drive. Again, it's an analogy, but between kind of programming and the network. Instead of writing that code, all you do is you train the network, which basically means you're making these links, you're giving weights to them. That's the whole thing. That's where the magic happens. And it's magic. It's very opaque. The network may decide to do something, and the network, meaning the algorithm that changes the weights during the learning period. After you're done learning, then you can plug in inputs here, and you get an output of some sort. So that's kind of how it works. Let's see what. So that's one. And there's various layers and various nodes. And what may happen is that some inputs may quiet some nodes. Just the way if let's say if this link has a big weight, like 1, and then this has but the input here is 0, this node might actually kind of stop half of the nodes on that layer, and then the other half talk about it, make a decision. Make a decision meaning their numbers go up while the others go down. So if I were a card and I need to recognize a child versus an old person, there may be some nodes that always fire up. In other words, they get a lot of, the number between 0 and 1 gets really close to 1 if it's a child. And there are other nodes, typically not the same nodes. Again, we don't understand how these networks work necessarily. That's the whole idea of explainable AI. But let's play with it a little bit. Let me see if I can. So here is a visualization, and I'm kind of go over it, of people from Google. I need to share my screen. So these are people from Google, and it's mostly kind of everything I tried to talk about. Maybe should have been better just move over there and show you. Try to understand neural networks. So it's from TensorFlow. That's a big Google package to do pretty powerful to build neural networks in Python. I'm not sure if they have it in other languages. So you can kind of see here the layer. So that's the input layer. In this case, there's 2 hidden layers, and then there's an output. They made it where we can see what's going on. And here is what's going on. I don't. And there's various things. See, the activation. I was telling you, there's a sum that happens when a node gets something in here. It sums up the input from x1 and the input from x2, and that's going to be this tan h. I wonder, is it tan hyper? I don't know what it is. Hypertangent? No, maybe not. It's a function. It has a definition. You can look at its graph and so forth. So the problem here is classification. Now, everything you see. Here is the color scale. So colors show data, neuron, and weight values. So if you see white, it's probably close to 0. And in this case, it's going from -1 to 1. So I was kind of misinforming you that it's 0, 1 is normal, -1 to 1 many times. But you don't want to have it more than that. So red is going to be, the redder it is, the more it goes to -1, and then blue is going to be closer to 1. The other thing about networks that makes it opaque is that normally there is an algorithm to initialize them, and that's a random thing. So it means that if you train the same network, or if you train a network on the same inputs, because you start with the randomized weights, you might get into different, they will look slightly different. So no two neural networks are exactly the same. Again, there's probably research into how to get them started. People look for different things. But one way to do it, at least naively, is to put some random values on the weights. Because you can't start with all 0 or 1, because then nothing happens. They're all maxed out, and they cannot learn. So as you can see, there's some, as I kind of go over each, it tells you the weight. I'm probably not going to do that most of the time, look at the actual weight, but you kind of get an idea. The data set, you can kind of see it here, and it's the points that are put in here. So basically, the input here, it's going to take the x and y coordinate. And notice that it's between 0 and it's between -6 and 6, the inputs themselves. But they kind of, the tan H will take care of them. And after the initial phase here, they kind of go. Everything inside the network stays between -1 and 1. So that's what this node does. Like I said, the input is always going to be superimposed on the output. So you kind of see what the network has been trained with and what is it learning. Right now, this network will say that all of these input points, so if you look in this area, it's blue. So it's going to be somewhere between in this. So it doesn't look like it. Most of it is kind of focused. It's around 0 right now. So it doesn't matter. If I look at a point, including this red one, the network will tell me that it's actually almost 0. If I look at this red point, if you look around it, the background is blue. So the network will classify this as being kind of bluish, but not very powerful blue. Okay, so I'll start running this. I'm not sure if you see as the network runs, that's what the output looks like. So you can see that what in effect was happening is that everything I give to the network in this reddish area is going to be classified as red. Everything I did to the network in the bluish area is going to be classified as blue, which is pretty good. Pretty much everything, if you look at the test loss, it's very low, and training loss is 0. So all the training things are classified correctly, so this network. But you kind of see what happens. If I give a new data point to this network, and I can stop it here. If I give a new data point to this network, and it's here, it will say it's red. If it's on the white, it basically won't be clear what it is. So that's this, and this is a combination of these two things on the output. So that's the second hidden layer, and then this layer right there. So you kind of saw how that network learns. If I move to different things and run it, this is how this network learned. So what it learned, it created different weights here and different weights here. So what this node does, it does this pattern, this node does this pattern, and they combine almost equal weight. And they show up in the output. Again, if something is in this area, it's going to be, the network wouldn't know if it's blue or red. Here is kind of going to tend to be bluish, but notice it's it's closer to 0. So white means I don't know what it is. The network is going to give you, because it's going to give you a number. the probability that it's red is this, the probability that it's blue is this. So everything white, it kind of gives you a low probability on both. So you don't know what it is. So that works. Let's see. Here's another one. That's pretty easy for the network to do. And again, both of them kind of did the same thing. This is going to be impossible for this network to classify. It kind of works. You see, there's a lot of error. That's kind of another way to think of this loss. Is it's trying, but it's not going to be able to do much. But you can see each weight. So some of these two are the link between this node and this node. You notice the weight is very low. This is very positive. And actually, according to this, it's not even between 0 and 1. Okay, like I said, at some point it gets transformed. I think in this example, it goes between 6 and -6. That would be, you can see there's this node has a big influence. This link has a big influence. That's how the network learned. And it's not perfect. It's very imperfect because the data is complicated. Because you see that these blue points are going to be classified as red because you see where the shape of the node. And then you can click on each of these nodes and see what they're trying to do. So each of them kind of draws a line with what's going on. And finally, kind of if you look at the input, I can also play with the input right here. I have an X1, which really, if you look at it, it ignores this node ignores the up and down component. So in other words, it's the X component that I cannot go here, so I'll have to. So this node goes from, it just ignores the Y. This node ignores the X. So it goes from -6 to 1 to +6. Again, I think that's why they're, well, they say this is -1 to 1, but it's actually 6. So this is the X component, the Y component. This is going to be, notice that it's all blue and in the middle is white. What function is that? It says right there, it's x1 squared. So it's the X component squared. That way you cannot have a negative number. It kind of gets blue, 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 white. When it gets to close to 0, you get a 0, and then it goes blue again. This is the Y component squared. This is the multiplication between X and Y, and you have a sine of X. You kind of see how the sign goes up and down, negative, 0, positive, negative. So 0, negative, 0, positive, 0, negative. And you get that effect. So that's on the X component. This is on the Y component. So what I can do is try and use different nodes here. See if I can get any better with this. And it's kind of learning. You can see that sometimes it goes back to what it learned. Now it's in some sort of an oscillation. Not sure if it will get out of it. Sometimes it kind of goes a little bit better. It kind of stopped, and it may be a little bit better than before. But notice that for the most part, they're almost not using the X component. So the most important ones are the sign of the X and Y components that are being used. And then this one is not as good. It has a very low weight versus this weight here. So this node decides. This is the decision maker. That's just adding something to it, but not much. Okay, so, and then that's not going to get any better here. So let's try and, I can probably get this out and have the same result. Other thing I can do here, add more layers. And let's see what this will do. Now, the more layers I have, notice it gets more complicated. It takes more time. You can see what each node, this node is doing this pattern, this node is doing this pattern. And then they're combining the patterns. It's not that great. So let's see. Let's add the original X and Y. So they're learning. So the way it learns, you actually show the same examples over and over again, and the network learns a little bit more. And sometimes it forgets what it learned, just like these are modeled by our neurons in our brain work like that. You have a neuron that's connected with other neurons. So that was the original. Add more. Gets a little bit better. Right now, this node here is the main decision maker. These other ones don't add much. But that's how you would learn about, and it's a network. You can kind of see how everything is connected to everything else. Okay, so that's one thing. Play with it if you want to learn about it, and that's what these guys have put it online. Let's go back to the slides. I don't really have to go back to the slide. We'll watch this video in a second. Well, let's watch it. Share my screen in a second, and let's see if we can skip this out. And let's see, share application. And instead of me playing with the, so I think this may be something that, maybe not. We had a paper at the beginning of the semester, but
Understanding how neural networks produce predictions remains a fundamental challenge. Consider this image classification model that takes an image as input and produces labels as output. In this example, the mountain bike image moves through the network and is correctly classified. However, in the following example, this bicycle is incorrectly classified as a truck. Existing work on interpreting neural network predictions for images often focuses on explaining predictions for single images or neurons. But predictions from state-of-the-art models are often computed based off of millions of weights optimized over millions of images. Such explanations can easily miss a bigger picture. We introduced Summit, an interactive system that scalably summarizes and interactively visualizes neural network feature representations for millions of images. Consider the white wolf class that by itself contains hundreds of images. In Summit, we create attribution graphs by passing all the data through the network to determine the top activated neurons and influential paths. Attribution graphs tell us what features the network is detecting and how those features are related. The Summit user interface tightly integrates 3 coordinated views for interpreting deep neural networks' learned features and their relationships. In the main view of Summit, we visualize attribution graphs for entire classes. This view is completely panable and scrollable, so let's zoom into one of the earlier layers of the network. Each vertex in the graph represents a neuron in the network. We show neurons using feature visualizations, synthetically generated images that maximize a specific neuron. For the white wolf class, this neuron appears to be detecting noses. We can confirm this by hovering over any neuron in the graph and showing examples from the dataset that maximize that neuron. Hovering over left to right on a specific neuron reveals different areas of the neuron's latent space. This layer has features to detect the left side of a dog face and the right side of a dog face. As we scroll up to go deeper into the network, we can see how the different low-level features combine to create higher-level features towards the output, such as this neuron that looks at white fur. Attribution graphs are completely dynamic. Users can adjust both the width and height of the graph, as well as filtering the neurons of a graph to drill down to the most important neurons and their connections. In the top left of Summit, we see the embedding view, a dimensionality reduction of every class in this neural network model. Users can zoom and pan in this view as well. By zooming in, we can see what other classes are most related to the white wolf class. Underneath the embedding view is the class sidebar. This is a sorted list of all the classes in the model and is directly linked to the embedding view above. The class sidebar encodes all the classes of the model with a few high-level summary statistics, and can be sorted based on the best performing classes, the worst performing classes, or by class similarity. Users can also search for any class in the network. In the Inception-1 network here, there's 1,000 classes from ImageNet. Let's go to the Tench class, a yellow-brownish fish. As we explore the Tench attribution graph, we see a lot of people part detectors, fingers, hands, and foreheads. It isn't until later layers where we see some neurons detecting brown and yellow types of fish. This is surprising because we wouldn't expect people to be an important feature for detecting fish. However, in the example images, we see the fish are typically being held by people and their fingers are in the frame, hinting that this model uses people to correctly classify tench fish from other types of fish in the network. Using Summit, users can make many discoveries like these by visualizing what features a network detects and understanding how those features are connected. To try Summit yourself, check out our open source demo in the link below.
I think Google started putting stuff in there for the next videos. I don't think that's... But that was an interesting thing. So I was telling you that these networks are sometimes opaque, and what they're trying to do, and you notice there's millions of images that these were trained on. So in order to detect the fish, what the network was doing was looking for people first that were holding the fish. So that's what the network learned. And in this case, we figured that out. In other cases, you don't understand why. And just looking at the weights, remember the previous playground, it's not going to tell you that much. So that's another way to try and visualize. And again, these are simple networks. So those two were more or less, these are kind of classical networks with layers that are all more or less manageable. And I'm going to go back to, I think I have one or more videos, but I'll go back to the screen, to the slides. I love it that I always have to scroll from the top. Well, so if we move beyond those networks that are classical and you kind of see the nodes, so forth, what they're doing, one very important one that's very, very popular with at least images is this idea of convolutional neural network. And here the layers, if you look at them, it's 224 times 224 times 64 nodes in this first layer, in the first convolutional block. And then it looks like, so I think times 64 goes this way. Then we have convolutional block 2, so they get smaller and smaller. And notice that blue is convolution plus, this is some way of so the convolutional neural network, it was a little bit of a hint in the video that was played previously. It looks at individual features of an image like noses. So if you look, so in order to find the nose, what you're doing, you're searching if imagine you have a picture. You're searching, it may have the sky in the background. You're looking at the sky. Obviously, there's not going to be a node there. But what the whole idea of the convolutional is that you break your image into squares. It's like chopping up into squares. And then each square, you're looking for certain features in that square. Do you find the nose in that square? Most of them, it won't be. There won't be only one nose. air. I mean, if there's 2 or 3 people in there, or 2 or 3 dogs, they will find 2 or 3 dogs in different places in the image. So that's kind of the idea, is take an image and chop it off into smaller pieces. That's the convolutional. And then you process each individual small piece in parallel, the con part. So they kind of get processed in parallel. And then the features here get smaller and smaller. So you break the image into smaller pieces, then you combine those smaller pieces, because I may find the nostril first. And in order to detect that it's a nose, I need to find nostrils and then whatever, if it's a dog, the shape of that dog and so forth. So we're looking for higher and higher level shapes. And then there's this max pooling, which kind of does a little bit of, what's the best way to describe it? It puts all the convolutional effort together and kind of say, what are we seeing? What features are here that are important? Because if it's the sky in the background, you don't care about that. You kind of ignore it. So that would be the max pool. It says, here are the important things that we found in the image. And then it goes and processes again, and then it does. So notice it keeps going this way. And then they start to be fully connected, but the number of the number here, so that imagine that this is an image. So what they're doing here, they're breaking down by 11 by 11 pixel. So they look at features that are 11 by 11 on the first, and then kind of break it down. It's like a sliding window that keeps sliding up, up and down, left and right. And I put here the number of the input layer has 0 parameters. The convolutional one has 608 parameters. Convolutional 2, 3,200, 48,000, 10,000, another 850. So that's what happens with this convolutional network. They are exponentially bigger. Every visualization that we looked at, the playground cannot handle that. There are way too many. Notice there's at least just doing about 60,000 edges in this convolutional network that looks at an image that's 227 by 227 pixels. They get bigger, your image gets even bigger. So I just put it's just another level of difficulty. So the normal neural networks are hard to understand. Guess what? Convolutional ones get even bigger than that. So I have a video here of a visualization tool that kind of allows us to look at okay. So let me do this. I can share my screen. And about 100 clicks later, again, I think both of these, you can play with them online, the videos that I showed you. Actually, since they're not talking, I'll try and kind of go over. This is the same architecture that we looked at. So there's layers and layers and layers. So we do convolutional, and then we kind of unite them. And then we do pooling and so forth. And here you can go through each and every layer and see what they are all being activated by, what feature of the image they're looking at. can kind of see, you can see the convolution, how that sliding window goes, and in parallel, they kind of determine all the features they go over. Here you can start to see some of the weights. So they're taking a 3 by 3 pixel and they're making down to 1. They make a single decision, so they look at a size 9 and then a size 1. On this image, the ladybug looks like pepper. I mean, you can see that the network predicts the bell pepper and then the second. If you want to learn more about this, it's right there again. That all three things that I showed you are interactive. I just use the video because I don't want to get lost. I mean, with Playground, I spend way too much time. If I do that for all three of them, we won't have time. And then the final thing that we are running into, so notice normal neural networks, I can talk a little bit and explain them maybe in 20 minutes. Again, not the math behind it, but the intuition. Then we go to images and it gets even more complicated. And guess what's next? This generative network. So all of these networks that we looked at so far, they're sometimes called classifiers. All they do is give you a class. It's a bell pepper, it's a nose, it's a white dog, a white wolf. The ChatGPT is not a classifier, it's a generative network. And in order to generate stuff like generate images, generate, you give it, in many of the classifier network, you give a lot of pixels, for example, or a lot of input and you get 1 or 2 things back. These are, you give 1 or 2 things back and the network keeps generating stuff. So the input is going to be a lot smaller than the output. So, and if I'm not going to talk about transformers, large language models, and all of that, but the idea is look at the size of the parameters. Model size, number of parameters in billions. So Google Switch Transformer, 1.6 trillion. OpenAI GPT, 170 billion. Do I have a visualization tool capable of looking at that? It's just I'm just shrugging by, if you're not in the room, I'm just shrugging. I don't know one that's able to do that. Everything that we looked at maybe deals with thousands of images. and those are scaled out. How would we figure out why are these networks doing what they're doing? I don't know. But as you can see, the number of weights, the number of links in the network is huge. And so kind of going through the 3 slides that I have here, or the 3 things: convolutional neural networks, 60,000. You can see, you can kind of learn more about how they operate, not necessarily what they do. Normal neural networks, they can be hairy, but not a lot, maybe 1,000 parameters. But then you go to large language models. Well, they're large because they're large. It's billions and billions, hundreds of billions to trillions of parameters. How do we visualize that? I don't know. So that's your problem. That's your project right now, between now and the end of the semester. I know some of you are gonna. I'm being. Please don't try that, because it's probably not enough time to deal. But you kind of see where we have graphs that are getting way too big to visualize. And that's pretty much the end of this section.